I will be talking about heating curves. Heating curves are a type of graph with heat on the x-axis and temperature on the y-axis. You will see a positive trend with this graph, since as you add more heat to something, its temperature will increase. The graph I have shown you is the heating curve of H2O. Let's take a look at it. Our journey begins at negative 20 degrees Celsius, where H2O is in its solid form, which is ice. What we're going to do is that we're going to add heat to this ice and try to eventually turn it into water vapor. We want to do this to study the heat properties of H2O. Let's start. We add heat to the ice and its temperature gradually increases until we reach 0 degrees Celsius. Then the temperature of the ice stops increasing. At this point, we're adding heat to the ice, but its temperature isn't increasing. The temperature line appears to be flat, even though the heat is increasing. So what's going on? We've reached the melting point of H2O. The heat we're adding isn't going to warm up the ice. Instead, it will go towards turning the ice into water. Yes, turning ice into water requires energy. This is called the heat of fusion. The heat of fusion for H2O is 6 kilojoules per mole, which means that we need 6 kilojoules of energy to turn 1 mole of ice into 1 mole of water. That energy comes from the heat we're adding. The temperature of the ice does not increase because the heat is being used to change phases instead of changing temperatures. At this point, we had only ice, but by adding energy, we turn all that ice into water at this point. And from there, we do the same thing. We add heat to our 0 degree water, and we see its temperature increasing. But then it stops increasing at 100 degrees Celsius. At this point, we've reached the boiling point of water. The heat we add isn't going to increase the temperature because it will go towards turning our water into water vapor. The energy required for this is called the heat of vaporization. For water, the heat of vaporization is 40 kilojoules per mole, which is higher than the heat of fusion. For this reason, we need more energy to turn our H2O from liquid to gas than from solid to liquid. This is why the constant line for vaporization is longer than the constant line for fusion. After we've added enough energy to our water, we reach this point where we have only water vapor. From there, we can add heat and its temperature will increase without further phase changes. One thing I haven't mentioned yet was the specific heat capacity. As you may know, water has a specific heat capacity of 4.184. However, ice and water vapor have lower specific heat capacities. For this reason, ice and water vapor have different sensitivities to heat. Ice has a specific heat capacity of 2.09, while water vapor has one of 2.03. Since their specific heat capacities are lower than water, they are more prone to changes in temperature, which is exactly what we see with the steeper slopes. So I hope that made sense. I want to clarify that heating curves are not just for water, and you may see them for other molecules. You can try to answer this question, which is a recreation of a question from an AP chemistry exam. Pause and take some time to answer this. Here's my answer. I hope you got something similar to it. That's all for now. It was a quick lesson, but thanks for sticking with me. Goodbye.